that we have Slido if they want to ask questions discreetly like that, otherwise they can stick their hands up.
Okay, thanks for the introduction. So today I will present our work for checking concurrent programs under the release and acquire semantics. It is a joint work with Paros, Fauzi, and Bang. We come from Uppsala University. So in this talk, we will address the problem of verifying safety property of concurrent programs under the release and acquire semantic. That is a fragment of the C11 semantic. So to start with, we will give some example to explain about the concurrent programs, about the execution trace and safety properties. And then I will summarize the state-of-the-art dynamic password reduction or DPOR algorithm that can handle the safety property for concurrent programs. Then we will talk about the release and acquire semantic and explain how we can define our DPOR algorithm for the release acquire semantics. Finally, we will see some experimental results and see some future work. So here, we consider the concurrent programs. So in concurrent programs, we can have several processes or threads. So you can see here, we can have two processes. And each process can have a write operation or read operation. For example, we can have the write operation x equal to 2. It means that we will write the value 2 to the set variable x. Another example, this is a read operation. We read from the set variable x and then store to the local register b. So in this talk, I will use x and y for the set variables, and I use a and b for the local register. So let's see what is the execution under the SC semantic or the sequential consistency semantic. So an execution, this is an interleaving of the operation from different processes. For example, here process P1 execute. Let process P1 execute first. So it executes the write instruction and then the read instruction. When we are doing the read instruction, we will read from the last write operation in the current execution. The reasons why, because we are under the SC semantic. So let process P2 do the same thing. It executes the write instruction and then the read instruction. So now for these concurrent programs, we want to check the safety properties. So by safety property, we can present by some assertion. And we want to check some assertion violation in the programs. For example, here we want to check at the end of the program whether we can reach to some state that a equal to 1 or b and b equal to 2. So in order to check the safety property, many approaches, they are based on reasoning about the trace of the concurrent programs. So a trace, we can understand it is a compact representation of the execution, and it can be applied for different memory models. So let's see the definition of the trace for the current execution. So we define the trace, that is a graph, contains the nodes and the edges. So the nodes, each node can be a read or write operation. And then there are 4 types of the edges. The first type is program order. This is the order of the instruction in the source code. The next one, this is a read from relation. It is a matching from a write operation to a read operation, saying that the read is reading from the write operation. The next one, this is a coherence order. This is the total order of the write operation to the same variables. So in this talk, we will use COX to present the coherence order for variable x, and we use CO for the union of all COX for all variable x. The last relation, this is a from read relation. We can derive this relation from the read from relation and the coherence order. For example, here we can derive a from read relation from a read to a write operation, and it is saying that the write is overwriting the value that is read by the read. So now we can formulate the SC semantic. Instead of using the interleaving way, we can present by an axiom that's saying that the SC semantic can be presented by the axiom that the union of program order, read from relation, coherence order, and from read relation, it is acyclic. So we see that this trace satisfies the SE semantic because we don't have any cycle based on program order, read from relation, CO, and from read. We give an example to say that we can use a trace to present for many executions. For example, here you see you can have a two execution, pi1 and pi2, and the main difference between the two executions, this is the order of the read operations. And all of them can be presented by the same trace. So now, after we know the concurrent programs, we see that how DPOR algorithm can be applied to solve the safety properties for concurrent programs. So we see that in order to check the safety property, we check the assertion violation. So the assertion violation depends on the position of the assertion. So it depends on the program counters. Also, it depends on the value of the local register. So there are two things. So because we know that the trace contains the program order and read from relation, so all of the DPOR algorithms, they will generate at least one execution per trace. So for example, here, for the previous concurrent programs, we have six different executions. And there are 4 different traces. So most of the DPOR algorithms, they will generate at least 4 executions. And the optimal DPOR algorithm, they will generate exactly 4 executions for trace. And this is the work has been done in Popo 2014. But now our observation is that in order to check the assertion, the main idea is we don't need to care about the coherence order. We just need to care about the program order and read from relations. This is our observation. So for example, here, in order to check the previous assertion, we can remove the coherence order in the trace. And by doing that, we can reduce from 4 traces based on program order, read from relation, coherence order, and from read relation to only 3 traces. And these 3 traces, they are different in program order and read from relations. So now by super optimal DPOR, our motivation is that we want to generate only one execution per trace with different program order and read from relations. This is our motivation of the work. So let's see. Before we come to our DPOR algorithm, we want to explain shortly the release and acquire semantics. This is a fragment of the C11 semantic. So we see that why we need weak memory model or release and acquire semantic, because we know that SC, they are the most simple and intuitive memory model for programmers. But it is often too strong, and it is not easy to obtain an efficient implementation under the sequential consistency semantic. This is why people introduce the weak memory models. So we see that weak memory models can appear in many applications. For example, it can appear in Intel x86 or IBM Power or ARM microprocessors. Or even it can appear in programming languages such as C11 or Java. So by using the weak memory model, we can obtain the efficient implementation. But we can also have unexpected behaviors. In this talk, we talk about the release and acquire semantics. It is a fragment of the C11 semantics. So let's see what is the release and acquire semantic. In order to explain, we give another example. This is a small example. Contain 2 processes. Process P1, write to Y and then read to X. And process P2, write to X and then read from Y. And at the end of the execution, we want to check the assertion that whether both processes can read from the initial values. It means A equal to 0 and B equal to 0. So this program, also known as the Decker mutex pattern or the single buffer programs. So the meaning of the this program that is under SC, we cannot violate these assertion violations. So now the array semantic, we can formalize the array semantic by the axiom that the union of program order read from relation COX and from read X is a cyclic for all variable X. You can see the difference between the array semantic and the SC semantic here. So let's see a choice that covers all executions that will lead to the violation of the assertion. So here we have 4 events or 4 operation. We have the program order. So now see that because process P1 read from the initial write. And this initial write is before any write to the same variable in coherence order. So we can derive a from-read relation. By the same reasoning, we can derive another from-read relation from read Y. So now we have the trace of any execution that will violate the assertion. Look to this J. We see that this J satisfies the array semantic. This because we don't have any cycle based on program order read from relation COX and from read X. You can see there is a cycle, but it's based on from read X and from read Y. So we say that this J satisfies the array semantic, but it is not satisfy the SE semantics. So now we come to our super optimal DPOR algorithm that can work under the array semantic. So there are 2 steps of our algorithm. First, we need to build the trace one after one. And when you have a trace, you will add the event one at a time. So there are 2 steps, and there are 3 properties of the algorithms that we can obtain. They are soundness, it means the algorithm only generates only valid trace. Completeness, it means the algorithm generates all valid trace. And optimality, it means the algorithm generates different trace. So we can obtain 3 properties here. So I will talk about if you are giving me a trace, I can extend the trace by adding the event one at a time. So in order to add the event to the trace, we want to generate only valid trace during the exploration. So we need to base on a mechanism with we name this by saturation. So the idea of the saturation here is that when you add the new event to the trace, you might need to add some coherence order that is necessary to guarantee the consistency of the trace. For example, here we are adding the read event, and this read event is reading from a write event write 2x. And also there is a write 1x that is before this read x in program order and read from relation. In this case, we need to add the coherence order from write 1x to write 2x in order to satisfy the array semantic. The reasons why, because if we don't do that, we can add the coherence order in other direction. And then we can obtain a from read x based on read from and CO. And then here we have the cycle based on the union of PO read from and from read x, and we will violate the array semantic. So we give some examples to explain about our saturation mechanism. The first example here, you have a trace, and we apply the saturation until we have a fixed point. So at the first step, we apply the saturation. We obtain a 1 COX. Then we have as a fixed point. And then we say that this trace, at this fixed point, it is a saturated trace. In another example, we have a different trace. We apply the saturation, but in this case, we don't add any necessary coherence order. The obtained trace is similar to the original one. So after we know how to do with the saturation mechanism, we can explain how to add a read event to the trace. So look here, we have a program with 2 processes. And then suppose we are doing this execution, we are trying to add the read event to the trace. So this is the current trace. First, in order to add the new read event, we need to add the program order. Now we need to calculate the read from relation for the new read event. So there are two cases here. The first case, we can read from the x equal to 1, and it satisfies the array semantic. In the second case, we see that we can read from x equal to 2, and also it satisfies the array semantic. So let's suppose that we want to read from x equal to 2 in these examples. We apply the saturation in order to obtain a saturated trace. Then we can continue exploring. So we add the last read operation. Now put the read operation to the trace and add the program order. We need to calculate the read from relation. And we see that because we already add the coherence order from x equal to 1 to x equal to 2, there is only one case. Here we must read from x equal to 2 in order to satisfy the array semantic. So in this talk, I will not talk about the way how we can build the trace one after one because of the time constraint. So we see some experimental results here. We compare our tool with two state-of-the-art tools that can handle the array semantic. The first one is a CDS checker, and the second one is RCMC. So we note that these two tools can handle a larger fragments of the C11 semantic, and also CDS checker also have some similar idea about the saturation. But in this experimental result, we see that CDS checker is not super optimal with respect to the trace based on program order and read from relations. And our tool we implement in a tool with the name tracer, and we are using the source code of CDS checker to implement this tool. So look to the first category of the benchmark. We have tested the three tools with the litmus test, with 8,000 litmus tests. So litmus tests are small programs that you have seen before, and they can be used to validate the tools under the weak memory models. So from the original litmus test, we generate the corresponding programs under the array semantic, and we can validate the tools under the array semantic. In the second benchmark, we test with the three standard benchmarks that are well applied in the Stateless model checking or DPOR algorithms. So here you see that these benchmarks, they are decided in the way that if you increase the number of processes here, you will have more conflicts between the read and the write operation. Therefore, you need to generate more execution in order to check the programs. So here we report the number of necessary execution that the three tools will generate in order to check the programs. We see that CDS checker for this benchmark, they generate a lot of executions comparing with RCMC and tracer. In this benchmark, RCMC and tracer, they generate the same number of executions. It means that there is no difference between the trace based on the program order, read from relation, coherence order, and from read with the one we are considered here in the paper. So we see that tracer is optimal with respect to the number of executions. We also report the running time, and we see that tracer is optimal or is very fast in performance. We can see other categories of the benchmark. For example, we have run the tool for the task competition benchmark. We can see the same observation that, for example, here, look to the Lamport benchmark. We see that tracer generates the less number of execution, and it is very efficient. Also, I have other categories of the benchmark. For example, some syntactic benchmark, some parameterized benchmark, and also some concurrent data structure benchmark. We see the same observation that the tracer always optimal with respect to the number of execution and the running time. So in conclusion, we have addressed the problem of verified safety property for concurrent program under the release and acquire semantic. We propose a new DPOR algorithm that can handle the verification problem for our concurrent programs under RA. For future work, we want to extend our work for other memory models such as the full C11, the SC, TSO, power, and AMP. Also, we can consider a weaker notion of chase. Or we can check the other safety properties such as race detection or liveness properties. Thank you.
Right, we have time for some questions.
I just have a quick question, more of a clarification. So optimal DPORs, they are very specific to the type of exploration the algorithm does. It's not really about just the number of executions that you have, but it's also the fact that when you're exploring, you never make mistakes, so you never reach these sleep set blocking executions. When you say super optimal here, it seems that you're also using a set solver. Like, what do you actually mean by super optimality, more than just because I myself have already claimed that we do super optimal DPORs before, so it's...
Yeah, so your questions related to the sleep sets in the DPOR algorithms. In our approach, actually we don't use a SAS solver. We use a similar exploration as in DPOR algorithm. But here we don't have the sleep set. We have another mechanism to handle the sleep set. We have something similar to the wake-up tree in the optimal DPOR. That we will maintain a data structure that we will need to explore in the future. We name this by the schedulers.
Any more questions?